Hey, this is the bell ringer we did today. Again, we haven't done it's like solving log inequalities in a while, so that's why we're gonna do this one today, right? So here we go. The first one is asking you give a log equation you ask to solve for a. Okay, and so if you recognize now, all I'm going to do is if I want to solve for a, right, I'm going to condense the log, and that's going to give me, is my pen working? Yeah, I like to use red. Okay, so I'm going to have log, okay, base b of a plus, I'm sorry, times 5, right? So it's going to be 5a times 5. Good. Sorry about that. What am I doing? Da-da-da-da-da. Okay. So when I condense this now, it's gonna be 5 times a, right? So I'm gonna get 5a equals c. Good, because there's a plus right there. That's multiplication now. And now what I'm going to do if I want to solve for a now, I'm going to write this in exponential form now. So okay, that's a b right there. That's going to be b to the c is equal to 5a, and then just divide by 5 on both sides. We get b to the c divided by 5. Okay, and the answer is D. Good. The next one asks you to, again, solve an exponential equation. And so the goal is to isolate the exponential part of it, right? But so I'm going to add 8 to both sides and then divide by 4, okay? So when I'm done now, that gives me okay. Let's do it in 2 steps. All right. So for folks that may not see it, okay. So I'm gonna get 4, okay, times 3, 2 to the x. Add 8 to both sides. That gives me what's that? 324 is less than equal to 324. Good. And then divide by 4 now. That should give me 81. So that gives me 3, 2 to the x is less than equal to 81. Okay, so the goal now, again, the goal when we have an exponential inequality, before we attempt to use log on both sides, see if you can write both sides with the same base. So 81 now, I can write this as 3 to the fourth. Good. And then that's less than or equal to 3 to the 2x. That's the first thing you want to do. If you can't do this now, then then use log on both sides, okay? And if I'm here now, we're just going to have 2x is less than or equal to 4, x is less than or equal to 2. All right? So that's the solution right there. And the next one now, the next one involving solving log inequality. Now, before I start solving this one here, now this question is broken down is into 2 parts. Before we start solving this, what if this was an equal sign right there? Okay, then I would condense, right? And since each term has a log, once I condense, now I'm going to drop log and then solve for x. That's how we do that, right? For because now it has an inequality now, what we're going to do is first you must find the initial restriction on the log equation. All right, it's going to be you're going to find out you're going to okay, so look back for a second. So when it's an inequality, first step is find the inequality, right? I'm sorry, find the initial restriction on the log equation. So on the first log term, right, I have x minus 3. So remember, the argument can't be less than 0, right? It cannot be 0 and it can't be negative, right? So therefore, this must be right. This one here must be must is good for values for x greater than 3. Okay. a max. How do you get that? Just simple. I just put x minus 3 is greater than 0 and solve for x, okay? And then this one now must be x is greater than negative 9. So overall now, what is going to be the restriction on this log before I start solving it, right? Well, remember this from class, and some of you guys can probably see what the answer is, right? For negative 9, and then for 3. So remember now, the restriction is going to be the shared where they have the same domain in common, right? So that's going to be x greater than 3. So the initial restriction is x is greater than 3. And that's what this part problem asks for. What is the initial restriction? Well, the answer is going to be A. Okay. Now, once you find the initial restriction, now put it to the side. Put it to the side because we'll come back to it later on. Now, I'm going to solve it like there's an equal sign there. I'm going to condense log, and then if I can drop logs, I drop logs, okay? So let me erase this for a second right here. And so now I'm going to condense log. There's a plus sign. Okay, that what I'm doing right now is the second part right here. Second part I'm doing now, okay? So let's do it down here now. So I'm going to condense the log, and so that's going to give me log of 5 times x minus 3, and that is greater than log of x plus 9. Good. Now drop the logs, and I'm going to have 5x minus 15 is greater than x plus 9. Solve for x now, you're going to have x is greater than 6. So now, once I solve the log, I have this restriction now. I'm going to compare this one to the initial restriction and see what is the shared domain. So I'm going to have a 3 here, x is greater than 3, and a 6 there. So where do I have the shared domain? So my answer is going to be x is greater than 6, okay? So the answer is going to be here, D. All right, so remember, when we solve log inequalities, there are 2 steps. You got to find the initial restriction, and then after you solve for x, that restriction get at the end, compare both of them, and that's going to be your final answer. All right. We also did this. We also did this problem in class today too. Let me find some space to do this really quick. I made this. I came across this on another problem, and I thought this was a good one. Okay. This was it right here. If I can remember it correctly, it went like this. Simplify this expression. Log. Okay. Oh, what am I doing? Log. Come on. Okay. Log. Let's see what it is. Base 2 of 32 plus log base 3 of 81. What is that equal to? Okay. This is log. Let's write it better. Okay. Log base 3. What is that equals to? Okay. Now, you can't condense it, all right, because they're different bases. So what you got to do now is work them separately. This right here, the first term, right? Some of you can probably see the answer, right? It's gonna be 5. So I can set this to log base 2 of 32. Set it equals to x, right? And that gives me now 2 to the x is equal to 32. 32 I can write as 2 to the 5th power. So 2 to the x is equal to 2 to the 5th power. So x is equal to 5. So this here, this first term right here, okay, this first term right here is equal to 5. Good. The next one now, same concept, guys. Same concept. Okay, it's going to have log base 3 of 81 is equal to x. And what is that equal to now? Again, some of you guys can see the answer already. 3 to the x is equal to 81. Right, 81 is a factor of 3. That gives me 3 to the x is equal to 3 to the fourth power. So that's 81 right there. Therefore, x equals 4. So again, this second term right here is equal to 4. So 4 plus 5 is equal to 9. Okay? So make sure if you see anything like that, you know how to do it. All right? So that's what, that was the kind of bell ringer we did. And we also had, hopefully this doesn't stop the recording. Okay, I have an issue with this stopping sometimes. Let's do this one real quick. Okay, so this is the FRQ we did today, and this is a good one because it is a piecewise function. All right, and we haven't done piecewise in FRQs, so you can read it. You can pause and read it. I'm just going to go straight to the answer. Okay, here's the key now. So from the FRQ, there are 2 points, right? 6 and 7, 6 and 6 to 7 right here, and the other one is 2 and 15. Okay. Now it asked me to write 2 equations. Now, what a lot of kids did in class today, they didn't realize this. Okay. They were using one function to write both equations. Well, you can't, all right, because they're separate domains, all right? So my points, again, my points are 2 and 15 as one, and the other one is 6 and 6 to 7, okay? So therefore, when t equals 2 now, which equation am I going to use, all right? Well, when t equals 2, I'm in this domain right here. Okay, that's between 0 and 6. So therefore, I'm going to use this equation right here. So therefore, 15 now becomes r of t. So I'm going to have 15 is equal to 7 times a, right? And that's 2 to the 2. But what is 2 to the 2? That's just 1, right? So therefore, I can write this as just 1 right there, or just 7a, all right? And the other equation now is when t equals 6. Well, when t equals 6 now, I'm in the second equation, second domain, right? So therefore, that gives me now 7 now becomes r of t. So I'm going to have now 7 is going to equal to negative 213.29. I'm going to run a space plus b, let's put it down here, b times ln of 6. All right, so that's both equations right there, guys. All right, so now solve for a and b. Okay, another mistake kids did in class, they were trying to put the points in Desmos, right, and try to get a linear regression. But we can't on this one because the points are for 2 separate functions. So if you put in Desmos, which linear regression are you going to use? Exponential, but then how you solve for this one, the second one then, right? So you can't really use, in this case, you can't really put the points in Desmos. So recognize now, solve for A is pretty simple right here. It's a simple equation. So therefore A is going to equal to 15 divided by 7, right? And you get a decimal right there. And the other one, this looks really complicated, but it's not. It's a simple linear equation. I have 6, 7 is equal to negative 213.28 plus b times ln of 6. Can I start this over? Okay, all right now. All right. So to solve for b now, I'm just going to add 6, 7 plus 213.29 and then divide by ln of 6. See, that's just equal to b right there, guys. And you put it in your calculator and you get b right there, okay? And so if you look down here now, that's what I did. Okay, that's b right there. And then when you solve it, you get your b and your a's right there. All right, so it's a good FRQ. All right, here B1 and B2, guys, I really skipped over, but it's just find the average change, all right? When t equals 2 and t equals 6. You don't have to solve for those numbers because t equals 6, it gives you. That is your output. So those it's going to be 6, 7 minus 15, all right? And then B2 is pretty easy. Okay, B3 now, I ask you, and I hope by now, sorry, I'm watching the news real quick. So you can read this, but let's on your own. But let's read B3 together now. Consider the values that result from using the average rate of change found in one. So when we say the values that result from using the average rate of change, what are these values? These are your estimate, right? But your estimates, where are you going to find your estimates? They come from the secant line. Okay? So they're talking about the secant line right here. They're saying consider the values that result from using average change, right? To estimate the number, or to estimate the number of students that have heard the rumors. That's your estimate from your secant line, all right? And they want to know, are these numbers now, are these estimate less than or greater than the number of students predicted by the model? Now, it's good to kind of sketch a graph, okay? So between 2 and 6 now, because it's a piecewise function now, I got to figure out which function am I going to use for this part. If I go back up here now, we notice that between 2 and 6, right, that's in this part of the domain right here. So therefore, I'm going to use this graph. And if you look at it now, this is an exponential, right? Right. It is 7 times a to the 2 over t, right? That's the exponential right there. And so if I sketch the graph now, here's again, just sketch a basic exponential function. It's a graph. It's a growth. All right. Just sketch a growth right there, and we're looking at between two. I put two dots now. All right. That's for 2 and that's for 6, and I draw my secant line between those 2 points, and that's so you can kind of visualize what's going on. Okay? And then it asks you now. So the question is now, if I find an estimate from the secant line, say right here, or any point between 2 and 6, right, is that estimate going to be greater than the values found from R? Yes, because the secant line is above, right, the R. So the answer is yes, it is greater. But now you got to explain that. Okay, and again, here's my explanation, guys. All right. Okay, this will not go up. I'm gonna hold it in place, okay, so you guys can see what I'm talking about. This thing is in the way, and I'm not sure to get it out of the way. But here I just explained that R, right? R is concave up, and the average change is increasing. You must say that, right? Get the other way. Then I'm gonna look at a secant line now. I'm gonna say the average change of the secant line is constant. All right. So let's use my left hand. Okay. So the average rate of change of the secant line is constant. Now, okay, I need to turn this TV off. Okay. My next part now is, again, the reason why I'm going to say that the estimate is greater is because the secant line is above R. But where is it? Where is the secant line above R? You must say that it's between 2 and 6, right? So from 2 and 6, the secant line is above R. I'm going to say that too. And then after do that, now in conclusion, I'm going to say therefore, oops, come on. Therefore, for any p between 2 and 6, right, the estimate will be greater. All right. So that's it right there. It's a good FRQ. I think if you can get through the first part, it's straightforward. All right. And then part C asks, R is value between 0 and 12. Explain how the range values of the function R should be limited. I can't show you on my tab on my iPad right now, but I graphed. What I did was I graphed this function right here. Good. I graph it in Desmos, and to graph it in Desmos, you just put R of x for the first equation, right? R of x in Desmos is 7. My A value is 2.142, and it's x over 2, right? And then the restriction is, now some of you guys do this differently. When I write x over 2, and then I put curly bracket, and I put 0 is less than equal to x is less than 6, close bracket. That's our graph. And there's no space between the parentheses and the curly bracket. There's no space. And I do the same thing for the other one. I graph it, and when you graph it, it looks something like this, right? I'm going to show you a rough estimate what it looks like. And so I can explain to you how to answer C. Is there more space? I can do this right here. I need some space. Okay, bear with me, guys. I'm trying to find space. When you graph that, right, it looks something like this. Okay, you're gonna have the first part of the graph, which is your exponential. So it looks something like this, curving up, and then the second part is a log function. And we know what a log looks like. It start looking like this now. Let's use a different color. All right, and then the second part of the graph looks like this. Okay, so that's a log function now. So if you look at it now, right, this graph keeps on going towards infinity. It just keeps on going up, right? So therefore, what is asking you now? Explain how the range must be limited. Well, if this graph is going towards infinity, that means that I'm going to have an infinite number of students, right? But you can't, right? So as the t-value increases, this graph is going to infinity. So you cannot have an infinite number of students. All right. So that's what I'm going to say, right? So look at my statement now. For t greater than 6, right? R is a log function. So from here, R is a log function that increases without bound. I mean, it goes to infinity. All right. There cannot be an infinite number of students. You can't have that. So therefore, there must be a finite number. So therefore, the range is limited to R of 12. Why 12? Because they tell you that. That's the domain, right? So the maximum number of students you can get is R of 12, which is 175. So you must explain that. Put that in your answer, right? They're telling you that the end part of the domain is 12. Therefore, my range is going to end at R of 12, which is approximately 175. All right? All right, guys. So that's the FRQ we did today in class. All right? Hopefully that helps you.